this section in part 9, we're just going to finish up our discussion on redox reactions with just going through a whole series of examples, some more practice problems to get through, pulling all the information together that we've been talking about in the previous sections. So let's look at our first question. So what are the oxidation numbers for each carbon in the following compounds: CH2O2, CO3 2-, and C2H4O respectively? So we'll do this one together, and then some of the other questions I'll have you tackle on your own first. So let's look at CH2O2. So we set this up the same way. We have one carbon, 2 hydrogens, 2 oxygens equals to 0 because it's a neutral compound. We know our hydrogen and our oxygen oxidation numbers. Hydrogen is +1, each oxygen is -2. So that means carbon needs to be a +2 value. For the carbonate ion, CO3 2-, we set it up the same way, but now we set the equal to -2, the charge of the polyatomic ion. Oxygen, again, is always -2. So that means carbon has to be a +4 in this case. And then for our last molecule, C2H4O, we break that apart. 2 carbons plus 4 hydrogens plus our oxygen. Again, hydrogen is +1, each oxygen is -2. That means carbon here is a -1 value. So as we can see here, the carbon has a variable oxidation number, and that is absolutely fine. There's no problem with having these different oxidation numbers for some of the other atoms that don't fall into our specific rules that we've set forward. We have the rules so we can help figure out what these variable oxidation numbers are. So it's absolutely fine that we came up with 3 different values for carbon in this example. So in this one, this goes back a little bit. Take a minute and identify which element is oxidized and which is reduced. All right, so let's look at what's happening with magnesium. Oftentimes when you look at a reaction like this, we can write our oxidation numbers either above or below the species to help identify what we have. So here we want to follow our rules, and we say that neutral elements are always given an oxidation value of 0. We'll start with that. For magnesium and hydrogen, hydrogen is a diatomic gas, so it naturally occurs as H2. We look in water, oxygen always has a -2 value. Hydrogen always has a +1 value. Let's go over to magnesium hydroxide. Again, oxygen is always -2. Hydrogen is always -1. That means our hydroxide ion is a -1 ion. We know that, and then we've got 2 of those, so that means the magnesium has to be a +2 charge. Now that we've gone through and identified all our oxidation numbers, now I can clearly see how they've changed. I can see that the magnesium has gone from 0 to +2, and the hydrogen has gone from +1 to 0. Notice not all of the hydrogen has changed. Some of the hydrogen has stayed +1 as +1, but some of the hydrogen did change, and that's fine. It is absolutely fine that some changed and some did not. It's important that as long as some changed, then we can figure out what's happened. And the hydrogen has gained electrons. So we see that magnesium has gone from 0 to +2. It has lost electrons, so that is oxidized. Hydrogen has gone from +1 to 0. It has gained an electron, so that is reduced. All right, so take a minute and answer this question. In the following reaction, identify the reducing agent. So just like we did before, let's go through and identify some oxidation numbers. In this example, we don't need to do them all because we don't have any exceptions for hydrogen and oxygen. So the H3O plus and the water we can ignore because the hydrogen and the oxygen there are not changing at all. So we don't need to do the oxidation numbers for those 2 species, but for the copper and the nitrogen species, we do need to do those. So copper on the reactant side, we give a value of 0 because it's a neutral element. On the product side, it's a monatomic ion, so it's a +2. The nitrogen in nitrate is a +5, and the nitrogen in NO2 is a +4. The coefficients in front, the 2 coefficients in front, don't matter, so I completely ignore those. I don't need to worry about those at all. So now that we've identified the oxidation numbers, we can see that copper has gone from 0 to +2. That means it's lost electrons, it's oxidized, and it is the reducing agent. So the correct answer here is A. All right, so let's look at this example. So let's identify the oxidizing agent. So here's a complicated example. This is a big reaction. This is probably as big as we're going to get and see in any of our questions. But we're going to handle it the exact same way. We're going to go through our rules, identify all the oxidation numbers that are present, and then we can figure out which species is the oxidizing agent, which was being reduced, which one is gaining electrons. Right? So let's start by identifying our monatomic ions. So hydrogen is a monatomic on the right-hand side, so that's a +1. Manganese is a +2. Again, the coefficients in front don't matter. Oxygen is a neutral species. That's an elemental form of oxygen, so that has a value of 0. Hydrogen in the peroxide is a +1. Here's our oxygen exception because we have hydrogen peroxide. So here oxygen has a value of -1. On the product side, water, that's really straightforward. Hydrogen is +1, oxygen is -2. For the permanganate ion, each oxygen is -4 or -2, excuse me. I have 4 of those, so for a -8 total, it's a -1 anion, so that means the manganese is +7. So if you don't follow that, let's just go through the procedure like we've been doing. So our manganese oxidation number +4 times our oxygen oxidation number equals our polyatomic ion charge of -1. Manganese oxidation number +4 times -2. Clearly manganese needs to be +7. Now that I've done that, I can see that the manganese is changing oxidation numbers, and also some of the oxygen is changing oxidation numbers. So, but what's really happening is the manganese is what we want to focus on. Here, the oxygens are changing. It's a little bit more complicated to follow which oxygens are actually changing to become going from a -1 to a 0. So we're going to not focus on that. It's the manganese that we really are interested in. That's a lot more straightforward. Okay. Last question. Which of the following reactions is a redox reaction? All right. So let's look at this one together. So we can see that this is a very similar reaction, but they're not the same. In the top one, we have a potassium ion plus a chloride ion going to potassium chloride. And in this bottom, we have a potassium atom and a chlorine atom going to potassium chloride. So we can see here in the top, if I look at oxidation numbers, I have a +1 for the K+, -1 for the chloride, and on the product side, +1, -1. There is no change in oxidation numbers, not a redox reaction. In the second example, I'm going from 0 and 0 for my potassium and chlorine respectively to +1, -1. Here my oxidation numbers are changing. This is an example of a redox reaction. Okay. We'll leave things here with redox. I've just got a couple sections left to talk about some of the calculations that we do with these types of questions that we've been talking about, and I'll get into that next time. Thank you so much, everybody.